To introduce heterogeneity in the groundwater flow, this is no problem because we simply need to modify the raster maps of the hydraulic properties to represent that kind of heterogeneity. For those, we're going back to the console. Of course, you can again do this using the graphical interface. I'm just doing it by the command line because it's more easier and for you more reproducible if I do this. So I'm defining here the similar region as we had in the previous example. And I'm introducing a new raster map, which I call mask, where I store all the geometrical information. So here it is pretty simply because the whole raster map mask is pretty much 2. So 2 is the value in each cell of this raster map. Besides some region between the column 20 and 60 and the row 20 and 35. So somewhere in the middle with a tendency towards the west. In this domain, I'm running one. I'm doing this because later it's easier, I mean, not in this specific simple example, but if you have more different structures, it is sometimes easier to store all the geometrical information in an extra raster map and then use this raster map to define the different hydraulic properties. So you're just lazy actually in trying to save some typing work. So we will generate this mask, but for right now we won't actually need it because we will first of all introduce all the different raster maps as we've done before. So pressure hat, the status, which cell directive, what kind of boundary conditions I want to apply. I will define the top of the unconfined aquifer. So again, I'm doing an unconfined simulation. I will introduce a null map, which is like the bottom boundary. And I will define the porosity of 15%, which we then replace for storativity. So, and now I'm introducing the heterogeneity in the hydraulic connectivity. And I'm doing this because I know, okay, for those values where the mask has the value 1, so in this little subdomain, this little rectangular, I want to have a reduced hydraulic connectivity than in the surrounding. And this is already it, right? But the benefit here of the mask is I can just simply say if mask equals 1, and I could continue and say if mask equals 2, if mask equals 3, if mask equals 4, and so on, right? I just simply advise the values. And the same you could do for porosity, for the top layer, and anything else. So this is a quite convenient way simply to do it, and that's why I introduce it here. So we're doing this here, and now we simply run the groundwater flow command as I've done it before. We hit enter and take some time to compute, and then we can take a look at the results. I want to look, okay, that looks interesting now, right? So for homogeneous, we layer, right, we didn't saw anything else than numerical noise in the y velocity. Now we have some decent numbers here, plus and minus. It's very symmetric. That's what we expect because we have a very symmetric number and domain, right? We can also take a look at the x direction. Now the legend is not adjusting. I'm not plotting the legend now every time, but we see here, okay, that looks different as well. You can clearly see the structure in the middle. And of course, in the pressure head, you're not directly seeing it. There's maybe a little shift here. You can see quite in the middle where the structure is. For clarity, I will also import the raster map mask so that you get an idea how it looks like. So this is pretty much it. So everything in yellow is the value 2, and simply here's my rectangular with the value 1 where I introduced heterogeneity. Right, so now this is, if you really want to know the flow velocity or the flow path here, this is kind of difficult to analyze. And therefore, there is an opportunity which actually call something like a quiver plot. So it means that the flow velocity is indicated by arrows, and the direction of the error and the magnitude, so the length of the error, gives you the idea about the flow field. So we can simply do this by calculating the two required raster maps. So one for the magnitude, which is pretty much well, the length of the vector based of x and y components. So this is simple linear algebra. And giving us the direction here as an angle, which is the tangents, the arctangents between the two components of the vector. Having this one, and now there is a new command in GRASS GIS, which is derust arrow, right? And we just simply give it a map and the magnitude map, right? And we want to have the arrows in the color of black. We only want to have it in every 20th grid point. We don't want to have any grid in the background, and I emphasize it by factor 50. That might be too much. We might see how it looks like. So that gives us okay, right? So now on the left you see these arrows, and you see how the water is flowing around, of course, this body, which is inhibiting flow. So in here the arrows are very, very small, right? And so the water is pretty much flowing around as you would expect, because we have a very low hydraulic conductivity in here. So as the same pressure is applying here, the flow velocity is much, much smaller than surround. So most of the water will flow around our obstacle and nothing will flow inside. And this is just one way here with the arrows to visualize it. You might, reduce them at the scale. So we could go to 30 and maybe even making less correct points, right? If I'm doing this one, we of course have to turn out the old map, and now it's it's less emphasized, less arrows, and you can see that they follow, of course, the same trend, so there's not much difference. But this is now a better visualization of the velocity in x and y direction.